The pressure at Titanic's depth exceeds 5,000 pounds per square inch. Imagine stacking 50 cars on your shoulders. In 1912, divers could only reach 90 meters deep, while Titanic lay at 3,800 meters. The technological gap was so vast that finding the wreck seemed impossible. Today, remotely operated vehicles explore the Mariana Trench to 11,000 meters, nearly 3 times Titanic's depth. This revelation makes the 73-year search seem even more remarkable when you understand what early explorers were truly up against. The challenge wasn't just about locating a shipwreck. It was about conquering the most hostile environment on Earth, the impossible mathematics of 1912. When Titanic disappeared beneath the North Atlantic waves in 1912, the world's most advanced diving technology consisted of hard-hat diving suits and hand-operated air pumps. Professional divers could descend to a maximum depth of 90 meters on a good day with calm seas. Divers risked nitrogen narcosis and hours of slow decompression at just 90 meters, making any deeper work unthinkable. Titanic rested at 3,800 meters beneath the surface, creating a technological gap that seemed impossible to bridge. The wreck lay 42 times deeper than the maximum diving depth of 1912. To put this in perspective, the difference between 90 meters and 3,800 meters was equivalent to the gap between a tall building and the peak of Mount Everest. Every meter of additional depth multiplied the engineering challenges exponentially. The pressure at Titanic's depth is hundreds of times greater than at 90 meters, so existing suits and pumps would collapse. Equipment would have imploded long before reaching 3,800 meters. Crushing force at the wreck site equaled thousands of pounds per square inch, enough to compress steel and instantly destroy any diving equipment from 1912. Even if engineers had somehow solved the pressure problems, the air supply requirements would have remained insurmountable. A diver at 3,800 meters would need compressed air delivered at pressures far beyond what manual air pumps could generate. The amount of air required would have demanded industrial-scale compression equipment that didn't exist. The technological gap extended beyond just diving equipment. Navigation systems in 1912 relied on celestial observations and dead reckoning. Ships determined their position by measuring the sun and stars, methods that worked reasonably well for surface navigation but provided no way to map underwater locations precisely. Even if divers could somehow reach the wreck, they would have no way to record its exact position for future reference. Communication systems presented another impossible barrier. Surface-to-diver communication in 1912 consisted of rope signal-specific tugs on the diving line that conveyed basic messages. Complex operations required the diver to surface and discuss plans with the surface crew. At 3,800 meters, even if the diving line could reach that depth without breaking, the weight of the rope itself would make communication impossible. The search for Titanic would require solutions to problems that hadn't even been identified yet. Engineers needed to develop new materials that could withstand extreme pressure, new propulsion systems that could operate in the deep ocean, and new navigation methods that could work without reference to surface landmarks. The challenges extended far beyond simple diving technology into fundamental questions about how humans could operate in environments that seemed hostile to all life. Recovery operations would have demanded even more advanced technology. Moving or lifting a 46,000-ton ship from the ocean floor required engineering capabilities that wouldn't exist for decades. The wreck would need to be located, mapped, and analyzed before any recovery could begin. Each of these steps required technology that was completely beyond 1912 capabilities. The 73-year search timeline reflected humanity's learning curve in deep-sea exploration. Early searchers weren't just looking for a shipwreck. They were trying to solve fundamental problems in underwater technology, material science, and deep-sea navigation. The wreck remained lost not because searchers lacked determination or funding, but because the required technology simply didn't exist. Every failed expedition contributed to the knowledge base that would eventually make success possible, but that success would require inventions that were decades away from being conceived. The mathematical impossibility of reaching Titanic's depth with 1912 technology meant that any serious search would have to wait for revolutionary advances in deep-sea exploration. Yet despite these overwhelming technical barriers, the human imagination refused to accept defeat. The same period that produced these sobering calculations about pressure and depth also gave birth to a remarkable collection of ambitious schemes from inventors who believed that engineering ingenuity could overcome any obstacle, no matter how formidable the physics involved. Wild schemes and desperate dreams. These inventors approached the Titanic salvage challenge with remarkable confidence, treating the ocean floor like any other construction site. The fact that a 46,000-ton ship lay crushed under extreme pressure seemed like a minor technical detail rather than an insurmountable obstacle. In 1914, a Denver architect proposed attaching massive electromagnets to a submarine that would descend to the wreck site. The theory suggested these magnets would locate Titanic's steel hull and provide the connection point for lifting operations. Once positioned, additional electromagnets would be lowered from surface barges to winch the entire ship to the surface. The estimated cost reached $1.5 million, equivalent to $35.5 million in today's currency. The plan completely ignored fundamental problems of transmitting electrical power to 3,800 meters depth and attaching lifting devices to a hull under 6,000 pounds per square inch of pressure. The magnetic attraction plan assumed Titanic remained structurally intact and accessible for equipment attachment. The inventor never considered that the ship's steel hull would be buried under decades of sediment, making contact impossible. He also failed to account for the fact that no electrical system from 1914 could operate at such crushing depths. The plan treated deep-sea recovery like surface construction, ignoring the hostile environment that would destroy equipment long before reaching the target. Another proposal involved filling Titanic's interior with millions of ping-pong balls to create buoyancy. The theory suggested that hollow plastic balls would displace water inside the ship, making it light enough to float to the surface. Inventors calculated that approximately 27 billion ping-pong balls would be needed to offset the ship's weight. The plan called for teams of divers to carry mesh bags filled with ping-pong balls through the ship's openings, systematically filling each compartment until the vessel achieved neutral buoyancy. The ping-pong ball scheme ignored basic physics principles that would have been obvious to anyone who understood pressure differentials. The balls would collapse under pressure long before reaching the wreck. The hollow plastic shells that provided buoyancy at surface pressure would be crushed completely under deep-sea conditions. Even if the balls could somehow survive the descent, the ship's interior would be filled with debris, sediment, and twisted metal that would prevent any systematic filling operation. Numerous other ideas emerged with equal creativity and impracticality. One scheme imagined freezing the ship into an iceberg using 500,000 tons of liquid nitrogen. Other proposals suggested using 180,000 tons of molten wax pumped into the ship, training whales to attach lifting cables, or deploying giant helium balloons that would somehow maintain buoyancy under crushing pressure. Each plan demonstrated a fundamental misunderstanding of how materials behaved under extreme conditions and how objects moved through water at great depths. These schemes seemed reasonable to inventors who had never experienced deep-sea conditions firsthand. Most proposals came from architects, engineers, and businessmen whose experience with construction and manufacturing led them to believe the ocean floor was simply another work site. They applied surface-level thinking to problems that required understanding of pressure physics, material science, and deep-sea engineering. The inventors had no reference point for conditions at 3,800 meters depth because no human had ever descended anywhere near that depth and returned to describe the experience. The focus on salvage operations revealed a crucial blind spot in early thinking about the Titanic problem. Every elaborate scheme for raising the ship assumed the wreck had already been located and could be accessed for attachment of lifting devices. The inventors spent enormous energy designing systems for moving a 46,000-ton object from the ocean floor while completely ignoring the more fundamental challenge of finding that object in the first place. The salvage schemes created a false sense of progress, suggesting that finding Titanic was simply a matter of choosing the right lifting method and providing adequate funding. This misplaced confidence delayed serious search efforts for years as investors and explorers chased impossible engineering solutions instead of addressing the basic question of where the ship actually lay on the ocean floor. The coordinate problem that would plague searchers for decades was being completely overlooked while inventors focused on elaborate recovery methods. The ocean covers vast expanses, and Titanic occupied a space smaller than a city block, somewhere in that immense area. Yet the salvage dreamers proceeded as if the ship's location was already known and confirmed, when in reality the coordinates everyone trusted would prove to be dangerously misleading. The coordinate deception. The coordinates transmitted during Titanic's final distress calls created a dangerous illusion of precision that would mislead searchers for over 7 decades. When the ship's wireless operators tapped out their last desperate messages on April 15, 1912, they provided coordinates that seemed to pinpoint the exact location of the disaster. These numbers became the foundation for every search effort that followed, creating absolute confidence that searchers knew exactly where to look for the wreck. The Marconi wireless telegraph machine aboard Titanic transmitted these coordinates during the ship's final hours as the vessel listed heavily to starboard and water poured through the damaged hull. The wireless operators remained at their posts, sending out distress signals that included their position calculated using the navigation methods available in 1912. These coordinates proved essential for the rescue operation, guiding the RMS Carpathia directly to the area where survivors floated in lifeboats. The successful rescue of 705 passengers and crew members seemed to confirm the accuracy of the transmitted position. The fundamental flaw in this reasoning became apparent only decades later when searchers repeatedly failed to find any trace of the ship at the transmitted coordinates. The coordinates marked where Titanic sent its final wireless transmission, not where the vessel actually came to rest on the ocean floor. The ship continued moving for more than 2 hours after the last distress call, carried by ocean currents and its own remaining momentum as it settled deeper into the water. During these critical hours, Titanic drifted steadily away from the position recorded in its final transmission. North Atlantic currents shifted Titanic miles from its sent coordinates. The same current system that had transported the fatal iceberg also pushed the sinking ship off its transmitted course. As the ship took on water and lost propulsion, it became increasingly subject to the current's influence. The massive vessel, already listing and partially submerged, offered significant resistance to the water flow, causing it to drift substantially from its last known position. The rescue of survivors provided the first concrete evidence that the transmitted coordinates were incorrect. When the Carpathia arrived at the distressed position, the rescue ship found lifeboats and survivors scattered across an area several miles from the coordinates given in the final transmission. The lifeboats had drifted with the same current that affected the sinking ship, but their lighter weight and surface exposure made them drift even farther from the original position. The pattern of survivor locations indicated that the disaster had occurred upwind and upcurrent from the transmitted coordinates. This coordinate discrepancy created a false sense of precision that actually hindered search efforts for decades. Early salvage companies and expedition leaders focused their efforts on a small area around the transmitted coordinates, convinced that the wreck lay within a few square miles of the known position. They invested enormous resources in detailed searches of this limited area, using increasingly sophisticated equipment to examine every feature of the seafloor near the distress coordinates. When these intensive searches failed to locate any trace of the wreck, searchers concluded that their equipment was inadequate rather than questioning the fundamental accuracy of their target coordinates. Coordinates were based on last radio fixed 2 hours before sinking and ignored drift. Currents moved the ship and debris field miles off, expanding the search zone from a pinpoint to hundreds of square miles. Instead of searching a clearly defined target area, expedition teams faced the prospect of examining vast expanses of ocean floor with no clear boundaries. The expanded search area multiplied the time, cost, and complexity of any serious attempt to locate the wreck. Navigation technology in 1912 relied heavily on celestial navigation and dead reckoning methods that were prone to significant errors. Celestial navigation involved measuring the positions of stars, sun, and moon to determine a ship's location, while dead reckoning calculated position by estimating speed, direction, and time travel from a known starting point. Both methods accumulated errors over time, and factors like wind, current, and human error could easily introduce mistakes of several miles in position calculations. The officers calculating Titanic's position during the emergency would have been working under extreme stress with limited time and deteriorating conditions, making errors even more likely. The drift patterns for sinking ships created additional complications that were not understood in 1912. As Titanic settled deeper into the water, different parts of the vessel experienced varying degrees of current influence. The superstructure remaining above water acted like a sail, catching current and wind that pushed the ship in directions that could not be predicted from surface observations alone. The ship's changing buoyancy and trim as it filled with water altered its response to external forces, creating a complex drift pattern that defied simple calculation. Having coordinates proved almost worse than having no position information at all because they created false certainty that delayed recognition of the real search challenge. The coordinates suggested that finding Titanic was simply a matter of reaching the known location with adequate equipment, when in reality the first task was determining where the ship actually lay among hundreds of square miles of ocean floor. This fundamental navigation problem would require entirely new approaches that combine systematic methodology with advanced technology to overcome the decades of misdirected effort. Beasley's Dynamite gamble. By 1953, marine salvage expert Frederick Beasley had spent years studying the Titanic problem and concluded that previous search efforts had failed because they lacked systematic methodology. Traditional salvage operations relied on divers and surface equipment that couldn't reach the depths where Titanic lay, but Beasley recognized that new sonar technology offered a different approach. His marine salvage company had successfully located several shallow water wrecks using acoustic methods, and he believed these same principles could be applied to finding the world's most famous shipwreck. In 1953, Beasley dropped dynamite to generate echoes, pioneering acoustic search but lacked resolution to locate Titanic. His revolutionary approach centered on using dynamite explosions to create controlled acoustic pulses that would map the ocean floor. The theory was elegantly simple. Underwater explosions would generate sound waves that traveled through the water column at known speeds. When these sound waves struck objects on the seafloor, they would reflect back toward the surface where sonar equipment could detect and analyze the returning echoes. The acoustic mapping technique represented a significant advancement over previous search methods because it could examine vast areas of ocean floor quickly and systematically. Traditional diving operations could only investigate tiny sections of seafloor at a time, while surface-based searches relied on chance encounters with wreckage. Beasley's dynamite method could survey square miles of ocean floor in a single day, creating acoustic maps that showed every significant feature in the target area. The explosive charges would be detonated in grid patterns across the suspected wreck site, building up a comprehensive picture of the seafloor topography. Working with explosives in the rough North Atlantic waters created dangerous conditions that tested the crew's skill and courage. The dynamite charges had to be lowered to specific depths using weighted lines, then detonated by electrical signals sent from the surface. Ocean swells and unpredictable weather made handling explosives extremely hazardous, as the charges could detonate prematurely if they struck the ship's hull or if electrical systems were compromised by seawater. The crew worked in shifts around the clock, maintaining constant vigilance to ensure that safety protocols were followed during every explosive deployment. The North Atlantic's notorious weather patterns added another layer of complexity to the operation. Storms could arise suddenly, creating waves that made explosive handling impossible and forcing the team to secure their equipment until conditions improved. The cold water temperatures affected the performance of both the explosive charges and sonar equipment, requiring constant adjustments to maintain optimal operating conditions. Ice formations posed additional hazards, as floating ice could interfere with sound wave transmission and create false echoes that confused the sonar readings. During the systematic survey of the suspected wreck site, Beasley's team began detecting acoustic signatures that generated considerable excitement among the crew. Several targets produced strong echoes that suggested large metal objects resting on the seafloor. The sonar patterns indicated structures with dimensions that could match portions of the Titanic's hull or superstructure. Each promising target was carefully mapped and recorded, with multiple explosive charges detonated around the suspected objects to build detailed acoustic profiles. The acoustic analysis revealed several objects that appeared to have the angular shapes and metallic properties expected from ship components. One particularly promising target showed dimensions consistent with Titanic's massive boilers, while another displayed the elongated profile that might indicate a section of the ship's hull. The sonar readings suggested these objects were partially buried in seafloor sediment, which would be expected after 4 decades on the ocean floor. The team spent days analyzing these targets, comparing the acoustic signatures to known specifications of Titanic's construction. While innovative, the 1953 sonar blast couldn't distinguish Titanic from seabed features, so the effort failed. The disappointing reality became clear as further analysis revealed that each promising target was actually a natural seafloor feature or debris unrelated to the Titanic. Rock formations created acoustic signatures that could mimic metal structures, while other shipwrecks and debris fields produced echoes that resembled sections of the famous liner. The vast expanse of the North Atlantic seafloor contained numerous objects that could generate false positive readings on the sonar equipment. Each false target consumed valuable time and resources, demonstrating the enormous challenge of distinguishing the Titanic from the countless other objects scattered across the ocean floor. The primitive sonar equipment available in 1953 simply lacked the resolution needed to provide clear identification of targets at such extreme depths. What appeared to be promising wreckage signatures turned out to be natural geological formations or unrelated debris that had accumulated on the seafloor over decades. Beasley's expedition ultimately failed to locate the Titanic, but his acoustic mapping techniques established principles that would guide future search efforts. The systematic approach to seafloor surveying and the use of controlled explosions to generate acoustic pulses influenced later expeditions. His work demonstrated both the potential and limitations of acoustic search methods, contributing valuable knowledge to the evolving field of deep-sea exploration. The failure taught important lessons about the technological requirements for deep-sea searches and the need for more sophisticated equipment capable of operating at extreme depths. The search for Titanic would require someone willing to push deep-sea exploration technology even further. Someone with the vision to develop entirely new approaches to the challenge of finding objects in the ocean's most hostile environment. Robert Ballard arrived at the Titanic challenge in 1977 with a reputation as a marine geologist who pushed the boundaries of deep-sea exploration technology. His work at the Woods Hole Oceanographic Institution had established him as someone who thought differently about underwater operations, approaching problems with engineering solutions that other researchers hadn't considered. Ballard had spent years studying the technical requirements for reaching extreme ocean depths and understood that finding Titanic would require methods that went far beyond traditional salvage approaches. His fascination with the famous wreck had grown into a professional obsession, driving him to seek funding and develop new technology specifically for this challenge. The 1977 expedition using the Alcoa Corporation's drill ship Sea Probe ended in catastrophic failure when the drilling pipe broke, sending 3,000 feet of pipe and $600,000 worth of electronic equipment to the ocean floor. The sonar systems, cameras, and remote control claw all disappeared into the depths along with the broken pipe section. This equipment represented the most advanced underwater technology available in 1977, making its loss a significant setback for deep-sea exploration efforts. The financial impact was enormous, equivalent to over $3 million in modern currency, devastating the expedition's budget and eliminating any possibility of continuing the search. The failure provided crucial lessons about the immense challenges facing deep-sea exploration at extreme depths. The pressure and stress loads at Titanic's depth proved more destructive than engineers had calculated, revealing fundamental flaws in the design assumptions that guided the equipment development. The complexity of operating sophisticated electronic systems at such depths became apparent as multiple failure modes combined to create cascading system breakdowns. The incident demonstrated that reaching the ocean floor was only the first challenge. Maintaining reliable operations under those conditions required engineering solutions that didn't yet exist. Sea Probe's broken drilling pipe taught Ballard that heavy mechanical systems were too vulnerable for operations at 3,800 meters depth. The catastrophic equipment failure revealed that complex mechanical systems with multiple moving parts could not withstand the extreme conditions at Titanic's resting place. The drilling pipe's structural failure under pressure showed that any successful deep-sea exploration system would need to be fundamentally different from traditional salvage equipment. The loss of the remote control claw demonstrated that mechanical manipulation systems were too fragile for the harsh environment of the deep ocean floor. The equipment failure forced Ballard to completely reconsider his approach to deep-sea exploration. The traditional model of extending mechanical systems from surface vessels to the ocean floor had proven inadequate for the extreme conditions at Titanic's depth. The broken pipe and lost electronics showed that any future expedition would need to rely on simpler, more robust technology that could survive the crushing pressure and corrosive environment of the deep Atlantic. The failure taught him that success would require abandoning complex mechanical systems in favor of more reliable alternatives. Ballard's response to this expensive failure revealed the determination that would eventually lead to his success in finding the Titanic. Rather than abandoning the search, he used the experience to identify the fundamental problems that needed to be solved before another attempt could succeed. The Sea Probe disaster guided the development of his Argo system concept, which would rely on a simple underwater sled rather than complex mechanical equipment. This new approach eliminated the vulnerable drilling pipe and mechanical claw systems that had failed so catastrophically in 1977. The lost equipment became valuable knowledge that informed future expedition planning. The failure demonstrated that deep-sea exploration required entirely different engineering principles than surface operations. The extreme pressure, corrosive salt water, and complete darkness of the deep ocean created conditions that destroyed conventional equipment. Any successful system would need to be designed specifically for these hostile conditions, with redundant systems and robust construction that could withstand forces that had crushed the sea probe's sophisticated equipment. The 1977 disaster also revealed the enormous financial risks associated with deep-sea exploration. The loss of $600,000 worth of equipment in a single equipment failure showed that Titanic searches required substantial financial backing and careful risk management. Future expeditions would need to account for the possibility of total equipment loss and plan accordingly. The high cost of deep-sea technology meant that each expedition represented a significant gamble with no guarantee of success. Ballard's analysis of the equipment failure identified the need for simpler, more reliable systems that could operate independently of complex mechanical connections to the surface. The broken drilling pipe had severed all communication and control links between the surface and the underwater equipment, demonstrating the vulnerability of systems that relied on physical connections across thousands of feet of ocean. Future designs would need to incorporate autonomous operation capabilities and wireless communication systems that could function even if physical connections failed. The lessons learned from the sea probe failure would prove essential to Ballard's eventual success. But the immediate aftermath of the disaster left the Titanic search community looking for new approaches and new funding sources. The expensive failure had demonstrated both the enormous challenges and the high costs of serious deep-sea exploration efforts. The search for Titanic would require someone with both the financial resources to absorb potential losses and the willingness to take extraordinary risks in pursuit of the world's most famous shipwreck, the eccentric billionaire and his monkey. Jack Grimm represented a unique breed of Texas oil tycoon, whose vast wealth had transformed him into a professional seeker of the world's most elusive mysteries. Before setting his sights on the Titanic, Grimm had already launched expeditions to find Noah's Ark in the mountains of Turkey, searched Scottish lochs for the Loch Ness Monster, and funded teams hunting for Bigfoot in the Pacific Northwest. His approach to these legendary quests reflected the confidence of a self-made billionaire who believed that sufficient funding and determination could solve any mystery, no matter how impossible it seemed to others. The Titanic represented his most ambitious challenge yet, combining his love of adventure with a puzzle that had stumped experts for nearly 7 decades. Grimm funded his expeditions through poker game backers and a substantial gift to Columbia University for sonar equipment. His unconventional financing methods reflected his larger-than-life personality and willingness to leverage any available resource in pursuit of his goals. The partnership with Columbia University transformed Grimm's amateur treasure hunting into a legitimate scientific expedition when he donated $330,000 to the Lamont Doherty Geological Observatory specifically for the purchase of advanced wide-sweep sonar equipment. This substantial investment provided him with 5 years of equipment access and the services of experienced technicians who understood how to operate sophisticated underwater survey systems. Eccentric oilman Jack Grimm even brought a map-pointing monkey, only to jettison Titan when scientists threatened to walk. The incident highlighted the tension between Grimm's unconventional methods and the scientific rigor required for deep-sea exploration. The researchers made it clear that they would not compromise their professional reputations by working alongside what they considered a publicity stunt. Grimm eventually relented, recognizing that the scientific expertise provided by Columbia University was essential for the expedition's success. The 1980 expedition launched from Port Everglades, Florida, on July 17 with C-Mark sonar equipment that surpassed anything previously used in Titanic searches. The side-looking sonar system was towed along the seabed on a cable, emitting acoustic pings in both directions to quickly map large areas while identifying unusual shapes or irregularities. When the sonar detected an anomaly, an onboard magnetometer determined whether the object was metallic, indicating a man-made structure rather than a natural seafloor feature. This systematic approach allowed the team to cover vast areas efficiently while maintaining the precision needed to distinguish between false targets and potential wreck components. The expedition faced constant challenges from the North Atlantic's notoriously harsh conditions. Bad weather plagued the mission for nearly 3 weeks, creating dangerous seas that made sonar operations difficult and sometimes impossible. Equipment failures occurred regularly under the extreme conditions, forcing the crew to spend valuable time repairing and recalibrating their systems. The vastness of the search area became increasingly apparent as the team realized that even their advanced sonar could only examine a fraction of the ocean floor where the Titanic might be located. C-Mark swept 500 square miles in bad weather, finding no wreck and teaching searchers to question the fundamental assumptions about Titanic's coordinates. The systematic approach revealed the enormous challenge of distinguishing between the countless objects scattered across the ocean floor and the specific components of the Titanic wreck. Rock formations created sonar, signatures that could mimic ship structures, while other debris from decades of maritime activity produced readings that resembled sections of the famous liner. Each promising target underwent careful analysis using multiple detection methods, but none proved to be pieces of the famous wreck. The expedition's findings led Grimm's team to question the coordinate assumptions that had guided search efforts for decades. The failure to find any trace of the wreck near the transmitted coordinates suggested that the ship's final position might have been significantly different from the distress call location. This realization forced the team to consider that ocean currents had carried the sinking vessel much farther from its last reported position than anyone had previously calculated. The theory implied that the Carpathia might have found the lifeboats more through luck than by following accurate coordinates to the disaster site. Based on these findings, Grimm expanded the search area for his following expedition to account for ocean drift after Titanic's final distress call. The expanded search zone reflected a growing understanding that the coordinate problem was more complex than simply reaching the transmitted position. The team recognized that finding the wreck would require examining hundreds of additional square miles of ocean floor, dramatically increasing the time and resources needed for a successful search. The 1981 expedition employed the more advanced C Mark II sonar device, which provided significantly better resolution than the previous equipment. Despite the improved technology, the team found that all 14 of the targets they identified turned out to be natural features of the ocean floor. The systematic elimination of false targets demonstrated both the effectiveness of the improved sonar and the enormous challenge of locating specific objects in the vast underwater landscape. On the final day of the expedition, the team discovered an object that appeared to have the distinctive shape of a propeller. This finding generated tremendous excitement as the crew believed they had finally located a piece of the Titanic wreck. The propeller-shaped object was carefully photographed and escorted with precision. Grimm announced that the Titanic had been found, though the scientist declined to endorse his identification without further verification. The discovery represented the most promising lead in decades of searching, but time constraints forced the expedition to return to shore before the mysterious object could be thoroughly investigated. The vanishing propeller mystery. Grimm's 1980 team found a propeller-like shape, but couldn't confirm it in 1983, apparently a sonar misread of natural rock. The grainy underwater photograph had shown what appeared to be a four-bladed propeller resting on the ocean floor, its distinctive shape clearly visible against the dark seafloor sediment. The object's dimensions seemed consistent with one of Titanic's massive bronze propellers, each weighing over 38 tons and measuring nearly 24 feet in diameter. The discovery had generated tremendous excitement among the expedition team, who believed they had finally located concrete evidence of the famous wreck. The 1983 expedition launched with upgraded equipment specifically designed to investigate this single target. The Robert D. Conrad carried advanced underwater cameras capable of capturing much clearer images than the primitive systems used 3 years earlier. The new camera systems featured improved lighting arrays and higher resolution sensors that could distinguish fine details even in the complete darkness of the deep ocean. The navigation technology represented a significant advancement with precision systems that could theoretically place the vessel within a few meters of any recorded coordinates. The systematic search began at the exact coordinates where the propeller-shaped object had been discovered, but the team found nothing that resembled the photographed object. The improved imaging capabilities provided crystal-clear views of the ocean floor, revealing natural rock formations and scattered debris with unprecedented detail. Every square meter of seafloor around the recorded location was examined methodically, yet the object that had generated such excitement and hope had disappeared without a trace. The precision equipment that had seemed so promising now confirmed that the team was searching in the correct location, but finding nothing. The shocking realization that the propeller-shaped object had completely vanished created confusion and disappointment among the expedition team. The coordinates were correct, the navigation systems were functioning properly, and the camera equipment was providing clear images of the seafloor. The team expanded their search area, considering that navigation errors might have placed them in the wrong location. But systematic examination of the surrounding area revealed no sign of the mysterious propeller. The object had simply vanished from the ocean floor as if it had never existed. The equipment malfunction emerged as one possible explanation for the disappearance. The 1980 camera systems had been primitive by comparison to the 1983 technology, raising questions about whether the original photograph had accurately captured what the team believed they had seen. The lighting systems used in 1980 could have created shadows or reflections that resembled a propeller when viewed through low-resolution cameras. Photographic artifacts or equipment distortions might have created an illusion of a propeller-shaped object where none actually existed, suggesting that the entire discovery had been based on misinterpretation of unclear photographic evidence. Misidentification represented another troubling possibility that the team had to consider. The deep ocean floor contained countless objects that could create shapes resembling ship components when viewed from certain angles or under specific lighting conditions. Rock formations weathered by ocean currents could develop curved edges that mimic manufactured objects. Debris from other shipwrecks or industrial activities might have created shadows or patterns that appeared propeller, like in the 1980 photographs. The team recognized that their excitement about finding Titanic components might have influenced their interpretation of ambiguous photographic evidence. Shifting ocean currents provided a third explanation for the object's disappearance. The powerful currents that flow across the North Atlantic seafloor could potentially move objects over time, particularly if they were not firmly embedded in the sediment. A propeller resting on the surface of the seafloor might be gradually pushed by current action, moving it far from its original position over a 3-year period. The team had observed evidence of current activity in the sediment patterns around the search area, suggesting that the seafloor environment was more dynamic than they had initially assumed. The failure to relocate the propeller-shaped object demonstrated the extreme difficulty of deep-sea navigation and object location even with improved technology. The vast expanse of the ocean floor made relocating specific objects incredibly challenging, particularly when those objects might be smaller or less distinctive than initially believed. The incident revealed that even promising discoveries could disappear in the immense darkness of the deep ocean, where precise navigation remained difficult despite technological advances. The vanishing propeller mystery highlighted fundamental challenges facing anyone attempting to locate objects in the hostile environment of the deep sea. Promising targets sometimes vanish due to misinterpretation of sonar data, equipment limitations, or the dynamic nature of ocean currents that constantly reshape the seafloor environment. The incident taught searchers that visual confirmation was essential before claiming any discovery, and that the ocean floor was far more complex and changeable than early expeditions had assumed. The repeated failures of civilian expeditions demonstrated that finding the Titanic required resources and technology far beyond what private funding could provide. The enormous costs, technical challenges, and high failure rates suggested that only institutions with substantial backing and advanced equipment could mount successful deep-sea exploration efforts. The search for Titanic would need to evolve beyond the realm of wealthy adventurers and academic institutions to succeed. Cold War submarines and secret missions. The breakthrough would come from an unexpected alliance between scientific ambition and military necessity. Ballard's secret Navy mission to locate USS Thresher and USS Scorpion first tested Argo, providing funding and technology for the Titanic search. The Navy wanted to find sunken nuclear submarines. Ballard used their month-long missions to pursue Titanic. The USS Thresher disaster in April 1963 had created an urgent Navy requirement for deep-sea location technology. This nuclear-powered submarine sank approximately 300 miles off the New England coast with all 129 crew members lost during sea trials. The submarine lay at depths exceeding 2,500 meters, requiring exploration technology that didn't exist when the disaster occurred. The USS Scorpion presented an even more complex challenge when it disappeared in May 1968 with 99 crew members aboard. This nuclear submarine vanished in the North Atlantic under mysterious circumstances that remain classified. Ballard proposed developing advanced underwater exploration systems that could locate both military and civilian wrecks at extreme depths. His plan involved creating technology that would serve Navy requirements while advancing his personal goal of finding the Titanic. The Navy agreed to fund development of the Argo system, a revolutionary, remotely operated vehicle capable of operating at depths up to 6,000 meters. This depth capability exceeded the requirements for reaching either lost submarine while providing the range needed to explore the Titanic's resting place. The Argo system revolutionized deep-sea exploration through its combination of advanced cameras, sonar equipment, and real-time communication capabilities. The remotely operated vehicle transmitted live video images back to surface control rooms, allowing operators to examine the ocean floor in unprecedented detail. Previous underwater exploration relied on still photographs or sonar readings that provided limited information about discovered objects. Argo's continuous video stream enabled immediate identification of targets. The development process involved extensive testing missions that provided Ballard with invaluable experience in deep-sea operations. The Navy missions to locate the USS Thresher and USS Scorpion served as training exercises for the eventual Titanic search. These operations taught Ballard's team how to navigate in the complete darkness of the deep ocean, how to interpret sonar readings from complex underwater terrain, and how to operate sophisticated equipment under extreme pressure conditions. The submarine missions revealed crucial information about how ships break apart and scatter across the ocean floor. The USS Thresher had imploded under extreme pressure, creating a debris field that extended across a wide area of seafloor. Ballard discovered that different materials behave differently when subjected to the crushing forces of the deep ocean. Heavy components like the submarine's nuclear reactor settled close to the main impact site, while lighter materials drifted considerable distances before settling. This pattern provided a roadmap for understanding how debris fields formed and how they could be used to locate main wreck sites. The debris field analysis revealed that lighter materials created searchable trails leading to the primary wreck location. Paper, fabric, and other lightweight debris drifted much farther from the impact site than heavy metal components. These materials followed predictable patterns based on ocean currents and their individual characteristics. Ballard realized that following these debris trails could lead searchers to the main wreck, even when the primary structure remained hidden or buried. This discovery represented a fundamental shift in search strategy from looking for the main wreck to following the evidence that pointed toward it. The ocean current patterns affecting debris distribution became a crucial factor in planning search operations. The same currents that had carried Titanic away from its reported sinking position also influenced how debris scattered across the seafloor. Ballard learned to predict debris patterns by understanding current flows and how different materials responded to underwater forces. The Navy's investment in deep-sea exploration technology provided Ballard with resources that far exceeded anything available to civilian researchers. The military funding supported development of advanced navigation systems, high-resolution cameras, and sophisticated sonar equipment that could operate reliably at extreme depths. The Navy's manufacturing capabilities enabled production of specialized equipment that could withstand the crushing pressure and corrosive environment of the deep ocean. The strategic importance of the submarine missions provided cover for Ballard's Titanic research while advancing military objectives. The Navy received detailed information about their lost submarines and valuable experience in deep-sea recovery operations. Ballard gained access to technology and expertise that made his civilian research goals achievable. The arrangement remained classified for years, creating the impression that the Titanic discovery was purely a scientific achievement rather than a byproduct of military operations. The debris field strategy that had proven successful in locating the USS Thresher and USS Scorpion would be applied to finding the Titanic. The Argo system had been thoroughly tested and proven capable of operating at the required depths. The Navy missions had provided the funding and experience necessary to mount a serious search for the famous wreck. With this foundation established, Ballard was ready to forge international partnerships that would bring together the most advanced underwater exploration capabilities available. The collaboration with Jean-Louis Michel, a French diving engineer from Ifremer, brought together the most advanced underwater exploration capabilities available on both sides of the Atlantic. The French National Institute of Oceanography contributed their revolutionary side-scan sonar technology, while Ballard provided his experience with deep-sea operations and access to U.S. Navy funding through the Office of Naval Technology. This partnership represented the first time that multiple nations had combined their resources specifically for the Titanic search. The French team's contribution centered on their sophisticated SAR system, which stood for System Acoustique Remorque. This advanced side-scan sonar technology produced detailed black and white shadow graphs of the seafloor that resembled near photographic images of the ocean bottom. The system operated by sending acoustic pulses in both directions from a towed vehicle, creating detailed maps of seafloor features across wide survey corridors. The SAR system represented a significant advancement over previous sonar technology, providing resolution that could theoretically distinguish between natural rock formations and man-made objects like ship components. In 1985, Ifremer's side-scan SAR sonar methodically mapped 150 square miles but found nothing, revealing sonar alone was insufficient. The French vessel Le Soleil executed a systematic survey pattern known as mowing the lawn, covering the designated search zone in parallel stripes to ensure complete coverage of every section of seafloor. Week after week, the French team continued their methodical survey, covering square mile after square mile of the Atlantic Ocean floor. The sonar operators became expert at interpreting the acoustic signatures produced by different seafloor features, learning to distinguish between natural formations and potential artificial objects. The expedition plan divided responsibilities between the French and American teams based on their respective technological strengths. The French team would conduct the initial sonar mapping phase, using their advanced SAR system to identify potential targets across the search area. Once promising targets were located, the American team would deploy the Argo visual system to confirm whether these targets represented pieces of the Titanic or natural seafloor features. This two-phase approach was designed to combine the wide area coverage capabilities of sonar with the detailed identification capabilities of camera systems. The mounting disappointment became evident as the French team neared completion of their survey without locating any definitive evidence of the Titanic. Despite their advanced technology and methodical approach, the sonar-based search had failed to identify the wreck that everyone believed lay somewhere within the designated search area. The French team had executed their mission flawlessly, covering the entire 150 square mile target zone with precision and care. Yet they had nothing to show for their efforts except detailed maps of empty ocean floor. The fundamental flaw in the sonar-based approach became clear only after the French team's failure to locate the wreck. Sonar technology, regardless of its sophistication, could not reliably distinguish between man-made debris and the countless natural objects scattered across the seafloor. Rock formations weathered by ocean currents could create acoustic signatures that resembled ship components, while actual wreckage might produce sonar returns that appeared identical to natural features. The technology that had seemed so promising for wide-area searches proved inadequate for the specific task of identifying Titanic components among the seafloor clutter. The sonar approach assumed that the main wreck would be large enough and distinctive enough to produce unmistakable acoustic signatures, but this assumption proved incorrect. The debris field that surrounded the wreck contained countless smaller objects that were individually too small for sonar detection, yet collectively represented a much larger target than the main wreck itself. Visual identification offered the only reliable method for distinguishing between man-made debris and natural seafloor features. The failure of the French sonar survey forced a complete strategy change with only 12 days remaining for the American Beasley expedition. The French team's thorough survey had inadvertently provided valuable information about where the Titanic was not located, eliminating large areas of ocean floor from consideration. Their systematic approach had also revealed the complexity of the seafloor environment and the challenges of distinguishing between natural and artificial objects using sonar alone. The partnership between French and American teams had demonstrated that international cooperation could bring together the best available technology, even when that technology proved insufficient for the specific challenges of deep-sea wreck location. The French team's meticulous work had covered every square mile of the designated search area with unprecedented precision, yet the wreck remained hidden somewhere in the vast darkness of the Atlantic Ocean floor. With time running out and conventional sonar methods proven inadequate, Ballard faced a critical decision that would determine whether the 1985 expedition would join a long list of failed attempts or finally solve the mystery that had eluded searchers for over 7 decades. Argo's eyes in the debris trail. Ballard deployed Argo's live video feed to follow scattered debris, eventually spotting Titanic boiler fragments, an approach sonar had missed. This decision represented a fundamental shift in search strategy that went against decades of conventional wisdom about deep-sea exploration. Previous expeditions had relied on sonar to locate targets before deploying cameras for confirmation, but Ballard recognized that the visual approach offered advantages that sonar could not provide. Cameras could distinguish between man-made debris and natural seafloor features with absolute certainty, while sonar readings remained open to interpretation and error. The remotely operated vehicle descended to depths of nearly 4,000 meters, sending back real-time video images through fiber optic cables that connected it to the surface control room. The researchers established a 24-hour watch schedule with teams of operators studying the camera feed for any signs of man-made objects among the natural seafloor features. Each shift lasted several hours, with fresh operators replacing tired ones to maintain constant vigilance as Argo methodically surveyed the target area. The new strategy focused on locating the debris field rather than searching directly for the main wreck structure. Ballard's experience with the submarine missions had taught him that debris scattered in predictable patterns across the ocean floor, creating trails that led to the primary wreck site. Lighter materials like paper, fabric, and small metal objects drifted farther from the impact point than heavy structural components, forming a debris trail that extended much farther than the main wreck itself. This approach transformed the search from looking for a single large object to following a trail of smaller objects that would eventually lead to the prize. Days passed with Argo capturing only natural ocean floor features as the 12-day deadline approached, and the team faced the possibility of another expensive failure. The pressure mounted as each hour brought them closer to the end of their mission without any sign of the debris field they desperately sought. The research vessel nor maintained its position above the search area, while Argo methodically covered square mile after square mile of empty seafloor. The operators struggled to maintain concentration as the monotonous parade of natural features continued without interruption. The psychological pressure intensified as the team realized they were running out of time and options. Previous expeditions had failed despite sophisticated equipment and careful planning, and this mission seemed destined for the same fate. The researchers began questioning whether their debris field strategy was fundamentally flawed, or whether they were searching in the wrong area entirely. The French team's failure to locate the wreck with their systematic sonar survey had eliminated many potential target areas, leaving fewer options for the visual search. The crucial moment arrived at 12:48 a.m. on September 1, 1985, when the first man-made objects began appearing in Argo's camera feed. The operators immediately recognized that these objects were different from the natural features they had been observing for days. The geometric shapes and manufactured surfaces stood out clearly against the organic patterns of the seafloor. The excitement in the control room was palpable as team members gathered around the monitors to examine the debris that had finally appeared on their screens. The debris trail became more concentrated and recognizable as Argo continued its survey of the area where the first man-made objects had appeared. Individual pieces of wreckage became visible, including fragments of metal, ceramic objects, and other manufactured items that clearly originated from a large vessel. The pattern of debris distribution confirmed that the team was following a trail that led toward a major wreck site. The concentration of objects increased as Argo moved in the direction indicated by the debris pattern. The team's experience with submarine wrecks provided crucial knowledge for interpreting the debris patterns they were observing. The USS Thresher and USS Scorpion missions had taught them how. Different materials scattered when ships broke apart under extreme pressure. Heavy objects like boilers and engines settled close to the main impact site, while lighter debris drifted considerable distances before coming to rest. The debris pattern visible in Argo's camera feed matched the patterns they had observed at the submarine wreck sites, confirming that they were following the right trail. The growing excitement reached a climax when a large, recognizable object appeared on screen that instantly confirmed the wreck's identity. The massive cylindrical structure with its distinctive shape and proportions matched the photographs of Titanic's boilers that the team had studied extensively during their preparation. The boiler's dimensions and design details were unmistakable, providing absolute confirmation that they had located debris from the famous ship. The object appeared exactly as it had it in the 1911 photographs taken during the ship's construction. The instant recognition of Titanic's boiler marked the successful conclusion of the 73-year search that had frustrated explorers and inventors since 1912. The team had found not just any piece of debris, but one of the most recognizable components of the ship that could provide definitive identification. The boiler's presence confirmed that the main wreck lay nearby, following the debris trail that had led them to this historic discovery. The discovery represented vindication for Ballard's decision to abandon sonar detection in favor of visual identification methods. The debris field strategy that had seemed risky when time was running short had proven successful where systematic sonar searches had failed. The combination of advanced camera technology, continuous monitoring, and experience gained from submarine missions had finally solved the mystery that captivated the world for over 7 decades. Yet the technology that seemed so advanced in 1985 would soon appear primitive compared to capabilities that would emerge in the following decades. What 2025 reveals about the search. The deep-sea exploration capabilities available in 2025 reveal just how primitive the 73-year search for Titanic actually was. 3 striking casts illustrate the technological revolution that has transformed underwater exploration. Modern remotely operated vehicles can reach depths exceeding 11,000 meters, nearly 3 times deeper than Titanic's resting place at 3,800 meters, while in 1912 divers were limited to just 90 meters in hard hat suits. GPS satellite navigation provides positioning accuracy within 3 meters anywhere on Earth's surface, eliminating the coordinate problems that plagued every search effort from 1912 through 1985, when searchers relied on dead reckoning and celestial navigation that could be off by miles. Artificial intelligence now analyzes sonar data in real time, automatically identifying man-made objects among natural seafloor features with accuracy rates exceeding 95%. Replacing the crude dynamite blasts that Frederick Beasley used in 1953 to generate acoustic echoes. The NOAA Ocean Exploration Cooperative Institute currently operates dozens of advanced underwater vehicles capable of conducting systematic surveys with accuracy measured in centimeters rather than the hundreds of meters that characterized early search efforts. Over 400 active ROVs operate worldwide, equipped with high-definition cameras, sophisticated sonar systems, and manipulator arms capable of delicate operations at crushing depths. These vehicles can operate continuously for months without surfacing, powered by fiber optic cables that provide unlimited electrical power and real-time data transmission. The success rate for locating specific underwater targets has improved from less than 10% in the 1980s to over 85% today. Modern technology could have located Titanic in weeks rather than the 73 years it actually took. The drift calculations that confused early searchers for decades can now be modeled precisely using computer simulations that account for ocean currents, weather patterns, and the hydrodynamic properties of sinking vessels. These models would have predicted Titanic's final position within a few hundred meters of its actual location, reducing the search area from hundreds of square miles to a few square kilometers. The coordinate deception that misled searchers for 7 decades would have been identified and corrected within days using modern navigation systems. The wreck's current condition in 2025 provides sobering evidence of the deterioration that has accelerated since its discovery. Iron-eating bacteria threaten Titanic's collapse by 2030, showing why preservation via film and 3D mapping is critical. The bow section remains recognizable with many preserved interiors, but the stern section has suffered catastrophic damage. The debris field around the wreck contains hundreds of thousands of items spilled from the ship as she sank, creating a scattered museum of artifacts across the ocean floor that continues to deteriorate with each passing year. Modern searches cost a fraction of what the 1985 expedition required, thanks to technological advances that have made deep-sea exploration commercially viable. Jack Grimm's expeditions in the 1980s required massive funding, while Robert Ballard's successful 1985 mission needed military backing equivalent to millions in current dollars. Today's technology can accomplish the same mission using commercially available ROVs and satellite navigation systems that operate at dramatically reduced costs. The democratization of deep-sea exploration technology has made underwater research accessible to universities, research institutions, and private companies that could never have afforded the massive expenditures required during the original search period. Satellite technology has eliminated the fundamental navigation problems that made the search so difficult for 7 decades. Modern GPS systems provide continuous positioning updates accurate to within meters, while satellite communication allows real-time coordination between surface vessels and underwater vehicles. Weather satellites provide detailed forecasts that help expeditions avoid the storms that plagued early search efforts. Ocean current monitoring through satellite observations enables precise calculation of drift patterns that would predict the Titanic's final position accurately. The mapping technology available in 2025 can create detailed 3-dimensional models of underwater objects with resolution measured in millimeters. Multi-beam sonar systems provide complete coverage of large areas in hours rather than the weeks required by earlier technology. Side-scan sonar produces photographic quality images of the seafloor that reveal details invisible to the primitive systems used during the original search. These advances make it possible to map entire wreck sites completely in a single expedition, documenting every artifact and structural detail with precision that would have been impossible during the decades-long search. Modern underwater vehicles operate with capabilities that would have seemed impossible during the 73-year search period. The E-Fulf Nautilus conducts expeditions using mapping sonars and ROV systems that can operate at depths exceeding 4,000 meters while providing live video feeds to researchers worldwide. These vehicles can manipulate objects weighing several tons, collect samples from precise locations, and operate in weather conditions that would have ended earlier expeditions. The fiber optic cables that power these systems provide unlimited operating time and real-time data transmission that eliminates the communication problems that plague historical search efforts. The technological revolution that makes Titanic's discovery seem routine today raises profound questions about the nature of exploration itself. The 73-year search timeline reflects not just the difficulty of finding a specific object in the vast ocean, but the fundamental challenge of developing technology capable of operating in environments that seemed completely inaccessible to previous generations. Titanic's 73-year search drove innovation and now lets us explore the deepest trenches as routine missions. Today's ROVs, Sonar, and AI represent leaps born from failures and successes of that quest. The techniques pioneered during the search, such as following debris trails and using systematic sonar mapping, have become standard practices in modern underwater archaeology. These methods now help locate shipwrecks and study submerged cultural resources across ocean depths that far exceed Titanic's resting place. The technology developed for this single wreck discovery transformed deep-sea exploration from an impossible dream into everyday reality. Modern expeditions to the Mariana Trench and other extreme depths rely on equipment that evolved directly from the systems created to find Titanic. The 73-year search ultimately achieved something far greater than locating one famous shipwreck. It opened Earth's final frontier to human exploration.